Welcome to a walkthrough of May 2018 TZ2 IB Chemistry Paper 1 High Level. Right, question 1. So this is a very typical question, number of atoms of oxygen in 2 moles of a compound, and you're given the Avogadro's constant. So what we do here is we take the Avogadro's constant, we times it by the mole, in this case, 2 mole. And because it's number of atoms, we look at how many oxygen atoms do we have in hydrated sodium carbonate? We have 3 plus 10, so we have 13. So then we times that by 13. So what you'll end up with, the Avogadro's constant times 26. Now what you do to shorten this is 6 times 26. That gives you 156. You know that this will be then converted to 1.56. So out of all the options, it's going to be D. Number 2. So what we've got here, we've got Na2SO4 at the beginning and then Na2SO4 at the end. We have volume, we have mass, and concentration. We are given these values, so we're given 100 centimeter cubed, we're given 1.42 grams, we're given the final concentration, 0.020, and what we have to work out is the volume of the final solution. So that's this one here. What is this? And it should be in centimeters cubed. Right. So if we have volume and concentration for both beginning and end, we can use this formula. C1 V1 equals C2 V2. Now to get there, we need to work out the beginning concentration. Okay, beginning concentration. Well, we know that volume, which we're given, and concentration, which we're trying to work out, they are linked by this formula. Okay, this triangle here. So let's try and work out moles then. How do we do that? Well, then we use a different formula. We use this one, mass Mr. Moles. Right, so we have our mass, 1.42 grams, divided by our MR, which is 142, given in the question, to get our moles, okay? So moles is 1.42 grams divided by 142. That will be 0.01. So then if we want to do concentration, we're going to do the moles, 0.01, divided by the volume, which is 0.1 in decimeters cubed. So that will give us 0.1. Right, well, we now have our beginning concentration, 0.1. So it's only now that we can use this formula. So it will be 0.1 times 0.1 equals 0.020 times something. Now this will give us 0.01 equals 0.020 times something. That something will be 0.5 decimeters cubed. Now we want that in centimeters cubed. So we're going to times by 100, and that's going to give us 500. Final answer of 500. Now that probably seems like a beast of a question, but the more you do these, the more easily all the equations will come to you, the quicker you'll be able to make all those links. So just keep going, okay? Final answer, C. Next question, what is the percentage yield? Right, so percentage yield is all about actual over theoretical times 100. So you'll notice that they are all times 100. So we can't narrow it down that way. So let's work out our actual and theoretical. We've got our beginning C2H5OH. That will be going to C2H4. We've got 5 grams. We end up with 2 grams. This is the mass. We also have the MR, so that's 46 here, 28 there. So what can we work out with this? Well, moles, of course. And we do that by dividing these two. Now we don't need to actually work it out. We just know that we will be putting this fraction over this fraction and then timesing it by 100 to follow our equation. So that will be B. Question 4. Electron transition that emits energy of the longest wavelength. Okay, so first of all, we are emitting, which means our arrow is going to go down. That's right. Emitting is down. Absorbing is up. So we can eliminate B and C. Is it going to be A or D? I like to use Richard Thornley's big jump, big energy, small wavelength. We want the longest wavelength, so we want the smallest energy and the smallest jump, which will be A. 4 is A. Right, next question. The graph shows the first ionization energies of some consecutive elements. Which statement is correct? Okay, so first thing we need to be able to do is identify this portion of the graph as the trend that we find in period 2 and 3. Okay, so it would go a group 1 element, a group 2 element, so on and so forth until we get to argon or neon. So if we were to follow that trend, it would be chlorine, sulfur, phosphorus, silicon, and this would be aluminium. We have a very steep drop here. Now that would be indicative of the fact that X is a noble gas. Okay, so in this case, if we went with period 3 here, this would be neon. There's a new shell which is further away from the nucleus, yeah, once we move from neon to sodium. And that requires less energy to remove the outermost electron, okay, because that's what first ionization energy is all about, removing the outermost electron. Okay, so less energy required, which is why we have that very steep drop. Knowing this, which statement is correct? That would be D. X is in group 18, noble gas. The other thing I wanted to mention here is you are required to know about two specific points and the reasoning behind them being at that level of ionization. So you need to know about this point here and this one here. So the first one, aluminium, obviously it goes down from magnesium. Why is that? Well, if we think about the electronic configuration, the outer electron of aluminium is in a 3p orbital. So that is a higher energy level, okay? It's further away from the nucleus. And so that has electron shielding from the lower energy levels, the 3s orbital in our case, which means that there's less energy that needs to be applied to remove it. Okay, so that's the reason for the aluminium. Yeah, so it's this distinction of removing an electron from a p sublevel rather than an s sublevel. And then on to the next one, the sulfur versus the phosphorus. I think that's really well illustrated by this diagram here. So sulfur is ever so slightly, I think, lower than phosphorus. And that is because of this here. We are removing an electron from a doubly occupied p orbital as opposed to a singularly occupied one. So there will be greater repulsion here. Greater repulsion. So it will be much easier to remove one of those electrons. So yeah, that's that. Just wanted to make a little side note because that comes up in both paper 1 and paper 2. So good tip here is to think about the electronic configuration as well as the orbitals. Next question. Which increase across a period from left to right? Okay, so I have a framework of just memorizing the trends very quickly here for paper 1 questions. So across a period, we have atomic radius, electronegativity, ionization energy, electron affinity, and ionic radius, okay? So the radii are at the top and they both go down across, whereas everything else goes up. And the very opposite happens down the group. So following that, the answer will be D. Ionization energy and electronegativity increase from left to right. Next one, which element is in the P block? Just have to look at your periodic table and know the P block, but that will be lead. Question 8. Part of the spectrochemical series is shown for transition metal complexes. So you have a bigger series in your data booklet. Which statement can be correctly deduced from this series? Right, so this is all about ligands. To give a bit of a backstory to ligands, Ligands are, first of all, Lewis bases. They are negative ions or neutral molecules that have lone pairs of electrons. Okay, so a ligand must possess a lone pair of electrons. The other thing is that they form complex ions using dative bonds, or also called coordinate covalent bonds. Yep, so we have these bonds forming between the ligand and the transition metal ion. So that's ligands. Now, I've mentioned that they form colored complexes. The very brief overview of this process is we have an incomplete d orbital because of the transition metal. The ligand causes a split in this d orbital, and light is absorbed as electrons transit to a higher energy level. Okay, so we have a split. We have 1, 2, 3, 4, 5. Yeah, so when the d orbital is split into 2, we have 2 that go at a higher level and 3 that go at a lower level. Then 1 electron will be raised from here to there. And basically what we're measuring is this gap here. Yeah, how big is that gap in energy? And that gap in energy is based on 3 things. The metal, right? What transition metal are we using? Its oxidation number, because we know that transition metal have variable oxidation numbers. And ligand type. And this is what this question is all about, the ligand type, okay? The higher on the series the ligand is, the greater this d orbital splitting will be. So that means greater charge density and a greater energy gap, okay? So ammonia will make this gap much bigger than the iodide ion, okay? Right, so looking at our options, water increases the PD separation more than Cl minus. No, because we're not looking at the p orbital, we're looking at the d orbitals. So it's not A. B, water increases the dd separation more than Cl minus. Yeah, that's true. C, a complex with Cl minus is more likely to be blue than that with ammonia. Well, if it's appearing blue, if the observed color is blue, then the color that it is actually absorbing is the complementary color, which on the color wheel is orange. So if it looks blue, it means it is absorbing orange. Now, orange is a lower energy form of light. So that would make sense, right? Because the chloride ion is a weaker ligand. So it's absorbing a lower energy form of light. So this answer seems quite good, in fact. Now, the explanation that I found as to why it's wrong is that copper chloride is yellow and copper with ammonia is actually royal blue. So I think it's a bit tricky because I, for example, did not have that knowledge at the time of my exams, just knowing that copper chloride is yellow and copper with ammonia is royal blue. We didn't do that many experiments. So it's tricky to say. If you have a better explanation, please write it down in the comments. As for D, complexes with water are always blue. Well, there are 3 factors that I mentioned that affect the color of a complex ion. Do you remember them? There's the metal, there is the oxidation number of that metal, and then there's the ligand. So, okay, water is the ligand that will affect the color, but there are also those 2 additional factors that could influence whether it's blue or a different color. Okay, so that's why it's not D. We've discussed why it's not C because the real colors are not what it says, even though going by the theory and the information that we're provided with in the syllabus, it could be correct. I might be mistaken, and we might need to know that copper chloride is yellow, in which case I apologize. Please add that to your revision to-do list. But in any case, the answer here will be B. Next question, what is the formula of magnesium nitride? Well, magnesium has a charge of 2+, nitride will be 3+, that's right. So we just put the charge on the opposite atom, so we get Mg3N2, and that will be D. Next question, which species has the longest carbon to oxygen bond length? Okay, we have CO, that is a triple bond. C1, 2, 3, O. This has a lone pair. This has a lone pair. CH3OH, if you have done organic, then this will be easy for you to draw out. If not, maybe not. And it has 2 lone pairs. What else? We have C, which I have put a diagram of here because it has a resonance structure. Again, if you've done organic, then it's quite easy to spot the resonance structures. And D, carbon, 2 hydrogens, and an oxygen with 2 lone pairs. So the longest bond will be the single bond, and the single bond in this case is with B. The triple bond in A would be the shortest bond. The bond order here would be 1.5, so it's in between a single bond and a double bond. And of course for D we have a double bond. Next question, what are the predicted electron domain geometries around the carbon in both nitrogen atoms in urea? Urea looks like this. And we have a lone pair there on both nitrogens. Why? Because nitrogen has 5 outer electrons. 1, 2, 3, 4, 5. Okay, that's why. So electron domain geometries, right, the carbon, that will be a trigonal planar. It has 3. 1, 2, 3. And yeah, the double bond counts as 1. So trigonal planar. And then the nitrogen atoms, they will be tetrahedral. We have 1, 2, 3, 4. Yeah, the lone pair counts as an electron domain. So that will be B. Next one, which molecule has an expanded octet? Well, we've just had a look at CO, so that's up there. What else do we have? We have CO2. We have SF2. And then the SF4. But now sulfur is in group 6. And so far we have 1, 2, 3, 4. So we need a lone pair. But that will mean sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. So it means it has an expanded octet, which means we've found our answer. D. Question 13. Which overlap of atomic orbitals leads to the formation of only a sigma bond? Okay, so SMP, that looks like this. Right, we've got that overlap there. What else? We have PMP. Now with PMP, you can get a side-to-side overlap, which would give you a pi bond. So that would be like this. That's a pi bond. Or if you have a head-on overlap, just like here, we would have a sigma bond. I'm not very good at drawing these, but you see the overlap there, and that's head-on, therefore sigma. Okay, that is side to side. Therefore, we get this pi bond. And then we have S to S. So that's one sphere, two spheres with that overlap there. So that would be sigma bond definitely. Up there, this will be a sigma bond definitely. This one depends on whether it's side to side or head on. So we're going to eliminate that. And it's going to be 1 and 3, which is B. Next one, which describes the reaction shown in the potential energy profile. Yeah, so to complete this, I'm just going to draw the line. Products have a greater enthalpy. So I'm going to eliminate this one, which says reactants have greater enthalpy. And this one. The reaction is endothermic. Great stuff. Next one. We have two 100 centimeter cubed aqueous solutions. One contains enthalpy change. We're looking at the enthalpy change. And we're told that the density of the solution is this, and the specific heat capacity of water is 4.18. So we'll be using Q equals mc delta T. We're trying to work out Q. We've got our mass, which would be 200, because we have two 100 centimeters cubed. So we can eliminate C and D. With D, we also have this plus 273. That would be to convert Celsius to Kelvin, but we don't need to do that. Why? Because it's temperature change. So whichever unit it's in, it will be the same. So you can also eliminate D for that reason. Now we have A and B, and the differences with the moles. Now, even though we do have two solutions and they both have 0.010 mole, we do not add them, okay? So we add volumes. We never add moles, okay? In this context, we add volume, we never add moles. So that will be B. Question 16, which value represents the lattice enthalpy of strontium chloride? So this is the lattice enthalpy. We're just going to work our way up and then down and see what we get. So because we're going against the first arrow here, we are going to change this sign. So it's not going to be minus, it's not going to be B or D, we have A and C, right? So we're changing that. Then we're adding 164, we're adding 243, so on until 1064. We're still going with the arrow as we go down, which means we don't need this. We don't need a sign change. So we are left with C. Which system has the most negative entropy change for the forward reaction? Most negative entropy change. So we are getting more ordered. Okay, we're moving towards order. So that means we're moving from lots of moles of gas to fewer moles of gas. So where do we have lots of moles of gas? First one, so that's the process for ammonia actually. Making ammonia. Fritz Haber, look him up, really interesting man. I did my EE on him actually. we've got 1 mole of gas, 3 moles of gas, 4 moles of gas in the reactants, and 2 moles in the products. That looks pretty good. What about the other ones? We're moving from 0 here to 1, so that gets less ordered. Nope, that would be positive entropy. Here we have 0 to 0, so no change. And here we have again 0 to 1. So our answer will be A. Next question, we have a potential energy profile for the reversible reaction, and we need to pick the arrow that represents the activation energy for the reversed reaction with a catalyst. Okay, so activation energy with a catalyst, we have 2 reactions. So with a catalyst, we'll be looking at this one. That's the activation energy for the forward. So that will be the activation energy for the backwards, which is C. Which factors can affect the rate of reaction? Particle size of solid reactant, yeah. Concentration of reacting solution, yes. And pressure of reacting gas, all 3. D. Last question of this video, we have reaction order graphs. These are all the ones that you need to know. So we have the 2 different types of graph. We have the rate graphs and we have the concentration graphs. The one that we're given is a concentration one. The line is going straight down, which means the reaction is 0th order in respect to X, which is C. A is incorrect because it should be indirectly proportional. The reaction cannot be first order. We don't know if the reaction is first order overall. We would have to see the graph for Y as well, because X reacts with Y. So we need to see the graph of both reactants in order to work out the overall order. The reaction is first order with respect to X. For D, well, it would have to be this graph. So that's it for now. Thanks for watching, and tune in for the next one.